Well, hello and welcome to Doc Onco Physics. Keith Onco here. Today what we're going to be doing is taking a look at a variety of rotational dynamics and specifically kinematics problems in rotational dynamics. And I'm going to do probably about 5 different problems. You can feel free to skip from one problem to the next problem. You don't have to watch them all in sequence, but you probably already know that. And the first problem that we're going to do is may not even seem like a rotational dynamics problem at all, but the problem basically is over here we have the Earth. Whoops. So we have Earth over here. I'm going to switch to black over here. And over here we have the Moon. And from the Earth, we're going to shine a laser beam, which starts at the Earth, right, and ends up on the Moon. And because a laser beam is a really good columnated beam of light, it doesn't diverge a whole lot like a flashlight would, but it does diverge a little bit, okay? And what we would like to know is what is the length of the beam, or what's the diameter of the beam going to look like? Because if I was looking head on at the Moon, you know, and I was close to the Moon, what I would see is you know, maybe a spot on the Moon, right, from that laser beam. And it's not going to be the tiny, maybe a few millimeter beam that takes off from the Earth, but it's going to be a much larger diameter beam that ends up being or shown on the Moon. And we'd like to know what that diameter beam would be. Well, like I said, at first this doesn't look like a rotational dynamics problem at all, but we can solve it with some of the concepts. If I treat the distance from the Earth to the Moon as a radius, okay, and that radius is 380,000 kilometers, okay, and I treat this as a circle, if you will, not a very good circle, but a circle nonetheless. What I have is I've got a radius, right, from the Earth to the Moon, and if I know the angle at which the beam diverges, then I should be able to figure out what this is using the formula, the conversion formula, x or s is equal to r times theta, right? This being theta, this being sort of an arc length if you want to take it to be that, right? And of course we know the radius because the radius would be the length from the Earth to the Moon, right? Let's say that the beam diverges at an angle of 1.4 times 10 to the minus fifth, that's a 5 there, radians. Okay, so that's our angle. So we know our angle, we know our radius, right? So we know this and we know this. We really ought to be able to get that. Okay, so let's do that. Now, our radius here is in kilometers. We don't deal in kilometers. We're going to have to convert that to meters. So 380,000 kilometers is 380 million meters. So x is going to be equal to 380 million meters times the angle in radians, so 1.4 times 10 to the minus fifth radians. And when we do this math, what we come out is for a value of x, and that would be, again, the diameter of the dot that would be shown on the Moon, or you could think of it as the arc length over here. And it would be 5.3 times 10 to the third meters. All right, so it would be a pretty big dot that would shine on the Moon. And again, this is not an obvious rotational dynamics problem, but you can solve it with the rotational dynamics equivalencies. Okay, so that's the first problem that we're going to solve. So the next problem we're going to take a look at is, let's see here, we'll make this red. A child has a ball, right, and this child is going to roll this ball to somebody else, over here. So it's going to travel from point A to point B, and the distance from A to B is 3.5 meters. Okay, so the distance is 3.5 meters. The child's going to roll the ball, so we're going to have rotational dynamics. The ball's going to rotate, right? It's going to rotate, but there's also going to be translational motion because it travels from here to here. So if the ball makes 15 revolutions in traveling from point A to point B, okay, what is the radius of the ball? We want to know the radius of the ball. All right, so that's ultimately what we want to know. All right, so what have we got? Well, we have the linear distance that the ball traveled, right? So again, we are going to use one of our conversion equations. We're probably going to use this one. X is equal to r times theta. All right. We know x, right? That's the value, the translational distance it traveled from point A to point B. Okay. It would also be the distance around the circumference. All right. How many circumferences, if you will, traveled from point A to point B. That's the same as the linear distance. Okay. So that's x. R is what we're trying to find. Theta we've been given, but we've been given it in a different format. We've been given it in revolutions. Well, we don't deal in revolutions. We deal in angles of radians. Okay, so 15 revolutions we're going to need to convert to radians. All right, so equals some number of radians. Well, what's the conversion from revolutions to radians? Well, if I have a round object here, and it revolves once from this point all the way to this point again, how many radians has it traveled through? Well, it's traveled through 2 pi radians. So 1 revolution is equal to 2 pi radians. All right, that's my equivalency. All right, so what I'm going to do is I'm going to multiply my 15 revolutions by 2 pi radians over 1 revolution. It's like multiplying by 1. Revolutions cancels out, and I'm left with radians. And so the number of radians that the ball is going to travel through is going to be 15 times 2 pi, which is about 94.2 radians. All right. So now I have my angle. I got my radius. I'm sorry, my angle. I've got my linear distance I can solve. So 3.5 meters is equal to r times 94.2 radians. Okay, I divide each side by 94.2, and I get the radius of my ball, and it turns out to be 0.037 meters or 3.7 centimeters, and that is the radius of the ball. Okay, so what do we do? Again, we use the equivalency formula. All right. The linear distance that the ball travels is equal to the radius of the ball times the angle through which the ball rotates. Okay, and that's all we did. All right, we haven't even really used any of the kinematics equations yet, but we will in the next example. All right, so let's get to the next example. Okay, in this example, that's not a flower that I've drawn there. It's my best attempt at the blades of a blender. And this problem is that the blades of a blender are rotating at a rate of 6,500 revolutions per minute. So my angular velocity, my initial angular velocity is 6,500 revolutions per minute, otherwise known as RPM, right? RPM equal revolutions per minute, okay? Whoops, per minute, all right. It then says the motor is turned off and the blades slow to rest in 3 seconds. So omega final is equal to 0. All right, and I'm going to make that in radians per second. All right, 0 radians per second. And it did it in a time of 3 seconds. All right, so I want to know a couple things. One is I want to know the angular acceleration as the blades slow down. And I would like to know the angle theta, how many radians that the blades traveled through, right, from the time it was moving at this speed to the time that it slows down. Okay, so let's see if we can figure that out. Well, first we're going to need to convert the initial velocity from revolutions per minute to radians per second. So we're going to have to do a couple of conversions. All right. First we're going to convert revolutions into radians. So we know that 1 revolution is equal to 2 pi radians. Okay. And I know that 1 minute is equal to 60 seconds. All right. So my revolutions cancel revolutions there. My minutes cancel minutes there. And I'm left with radians per second. And I still have to do the math to figure out what that is. So when I do that, the answer is about 681 radians per second. All right, so it's moving pretty quick. All right, so I want to know alpha. Well, to get alpha, I can use this equation right here, right, and just rearrange it so that it is equal to omega final minus omega initial divided by time. All right, and that is omega final is 0 minus omega initial, 618 radians per second, divided by the time, which was 3 seconds. And when we plug that into the old calculator, we get, it looks like I made a mistake here. I transposed my numbers. This should be 681. As you at home probably figured, that should be 681. And I transposed them to 618, so I apologize for that. But when we do the math here, 0 minus 681 divided by 3 is negative 227 radians per second squared. That would be the angular acceleration. It's negative because it's slowing down. It's a deceleration. Okay. Now, we would now like to know the angle through which the blender went, right, in slowing down from 6,500 RPMs to 0. Well, if I want to know the angle, it looks like this would probably be my best bet right here, right? I know my initial velocity, right? I know my acceleration, I know my time, so I can figure that out. So let's see what we got. The angle, and we'll use the initial angle to be 0 because we can do that. So theta is going to be theta 0 times t, so it's going to be 681 radians per second, times t, which is 3 seconds, plus a half times the deceleration, which is negative 227 radians per second squared, times the time squared, which is 9 seconds squared. And when we do this math, let's see what we get. Let's see, we get 1854 radians here, plus a negative 9193. And when we add those together, we about negative 7339 radians. And the negative sign just indicates the direction of the movement, of the motion, direction of the acceleration, right? So it will move through 7,339 radians and slowing from 681 radians per second to 0 radians per second. All right, so that's problem number 3. Let's do one more problem and see what that has to tell us. All right, so in this problem we have another thing that looks like a flower, but this time it's a cooling fan. And it says a cooling fan is turned off when it is running at 850 revolutions per minute. So the initial velocity is 850 revolutions per minute, right? And we're clearly going to have to convert that to radians per second. Our final velocity is 0 since it is turned off, right? And it turns 1,500 revolutions. So theta is equal to 1,500 revolutions in going from 850 revolutions per minute to 0. Okay, and we would like to know what alpha is, the angular acceleration, and how long in time it actually took to turn off. All right, so let's see if we can figure that out. All right, first we're going to have to convert our 850 revolutions per minute into radians per second. All right, and let's see what we get. So again, 1 revolution is 2 pi radians, and 1 minute, whoops, is 60 seconds. And when we do this math, we get 89 radians per second is our initial velocity. Our final velocity is again 0. And we also are going to have to convert, right, our revolutions, right, to radians as well. And so again, 1 revolution is 2 pi radians. And when we do that math, we get 1500 times 2 pi is 9,425 radians. Okay, so we know theta. All right, we're looking for alpha. So which equation is going to get us that? Well, we have an alpha in this equation here, all right? So we're looking for alpha. We have initial, we have final velocities, but we don't have time yet. So that's not going to help us. This equation, we have theta, all right? We have initial velocity, but again, we don't have alpha and we don't have time. So that one's not going to help us. But it looks like the very last one here may help us. We have final velocity, initial velocity, and we have our change in radians, right? It goes from, the change in radians is 9,425. That's the number of radians that this traveled through from going from final, initial velocity to final velocity. Okay, so we can use the last equation there. So let's do that. So omega final squared, which is 0 squared, is equal to omega initial squared, which is 89 radians per second squared, plus 2 times alpha times, right, the number of radians that it goes through, which is 9,425 radians. All right. So we square 89 and we get 7,921 radians squared per second squared plus, let's see here, it says 850 alpha is equal to 0. Okay, if I move this to the other side, I get negative 7921 radians squared per second squared is equal to 18,850 times alpha. I divide each side by 18,850 and I get alpha equal to negative 0.42 radians per second squared. So it takes some time for this thing to slow down, right? Or it's probably going to take some time for this thing to slow down. So this is negative 0.42 radians per second squared. Whoops, second squared. Okay, now we'd like to know how much time it took. Well, if we look at the top equation up here, we have final, right? We have initial velocities, initial velocity, final velocity. We have alpha now, we can get t. All right, so final velocity is 0, is equal to the initial velocity, which is 89 radians per second, plus alpha, which is negative 0.42 radians per second squared, times time. All right, I move this to the other side, and I get negative 89 radians per second equals negative 0.42 radians per second squared times time. When I divide each side by, that's an equal sign there. When I divide each side by negative 0.42, I get about time equal to 212 seconds. Okay. All right, so these are kinematics problems for rotational dynamics. Okay, they're very similar to kinematics problems in a linear sense, except that things are spinning around, and so our variables are somewhat different. The only way you get good at these is by doing them. So let's do one more example. Let's move the screen down a little bit here. And in this example, we have a farmer in there, an old style well, a crank here. All right, here's a handle, and our farmer needs to let the bucket down into a well here so that they can get some water. Okay, so this is, all right, some kind of a circular object here. There's a handle here, and this person can turn the handle clockwise and lower the bucket down into the water. And there's rope that is wrapped around the outside circumference of the wheel there. Okay, so the farmer on the old style farm lowers a bucket into the well to get some water. She turns the crank 20 full revolutions. All right, so theta is 20 revolutions. Why is that theta? Because she turns the crank on the wheel 20 full revolutions. Well, revolutions is equivalent to an angle. Okay, so it should be 20 revolutions. Okay, and the bucket descends 10 meters into the well. Okay, so the bucket goes down 10 meters into the well. We want to know what the radius of the wheel is that gets turned. So we want to know the radius. All right, we have x, right, the linear distance that the bucket traveled, and that's 10 meters. Right? Now, how do I know this is the linear distance? Well, all of this rope here was wrapped around the wheel. As the wheel turned, the rope was let out from here all the way down to wherever the bucket landed, which is 10 meters later. So we have our equivalency formula, all right? X is equal to r times theta, all right? So we can get r this way. Well, we got to convert from revolutions to radians, so we're going to have to multiply this by 2 pi, and when we do that, 20 times 2 pi is, 20 times 2 times pi is 125.6 radians. Okay, and now we can just plug things into the equation that we have. So 10 meters is equal to r times 125.6 radians. All right, I divide 10 by 125.6, 25.6, and I get 0.079 meters as the radius of my wheel, or 7.9 centimeters. Okay, so this again is not really a kinematics problem. This is a problem where I wanted to know the linear distance, right, of a rope that was wrapped around the wheel, how far that rope is going to travel if it's allowed to descend down into the well. Well, I hope that helps, and I hope you have a great day.